Let us now look at another example of an algorithm in MapReduce, image processing. Image processing involves the application of some operation on images. These operations may be feature extraction, application of some filter, etc. Images are typically represented as a 2D matrix of color values that can be binary, grayscale, or RGB or CYMK color values. These operations themselves are typically matrix operations. Hence, image processing can be a computationally intensive process, particularly for large images or a large number of images. Let's take a look at an example. In Sobel edge detection, a special operation is applied on an image which extracts the edges of the image. How do we speed up image processing? There are two ways. For large images, the operations within an image can be parallelized. In this technique, a large image would be split into smaller sub-images and the image processing operation would be applied to each sub-image in parallel. The sub-images would then have to be stitched together to get the final processed image. The other strategy is to parallelize operations across images. This is a feasible approach when the size of an individual image is small, but there are a large number of distinct images to process. Let us look at a naive MapReduce implementation of an image processing system in MapReduce. In the naive implementation, we send each image file to its own map task, which then processes each image independently and produces the output. Please note that a reducer is not required here, as the computation can be applied on each image independently. There are a few problems with this approach. When we have a large number of small images, say 1 million images, we have 1 million map tasks, which may take a substantial amount of time to finish on a cluster. A MapReduce cluster typically has a fixed number of slots, say 2 slots per node. Each map task comes with overheads which may actually exceed the actual computation required. In addition, HDFS is not efficient in dealing with small files. Hence, to speed up the computation, there should be some way to combine multiple files into a single file. Hadoop makes available a special format called sequence file, which can be used to combine multiple files into a single file. Hence, a sequence file that contains all the images to be processed can be created using the tools in Hadoop. A sequence file that contains all the images to be processed gets split into individual blocks by HDFS. These blocks will now be sent to individual mappers, which can iteratively process multiple images and write them to disk. This technique can greatly speed up the processing of images, at the expense of some pre-processing where the images have to be combined into the sequence file. As an example, we can look at the Sobel edge detection algorithm as implemented in Hadoop MapReduce. Since this is a map-only application, we will only present the map class as shown on screen. The map class is declared as image_p_mapper. It expects input in the form of text, bytes writable, where text corresponds to the name of the file and bytes writable is the binary contents of the file. The map outputs are the same as the map inputs. Within the class, we define two float arrays, x_kernel and y_kernel, to be the Sobel operators. Now we have the actual map function. The function is simple. We simply take the bytes writable value and read it as an image. Once it is read as a buffered image object, we apply the two Sobel kernels to the image. The final operations within the map function simply assemble the output value in the form of bytes writable and is written as the output of the map operation. There are also cases where a single image is too large to fit within a single HDFS block, and hence it spans multiple blocks. In this case, we have to split the image into multiple sub-images and assign each sub-image to a mapper. Once the mappers have processed their assigned sub-image, they can send the data along with the relevant key to a reducer, which can assemble the final image.